want to welcome everybody to part 2 of What's New in SolidWorks 2017 presented by DASI Solutions. Today we're going to go ahead and cover the second section of our 3-hour presentation. I'm your presenter, Darin DASI. I'm a 20-year veteran with DASI Solutions and SolidWorks, and it's been a fantastic ride, and we have our customers to thank for that. So for all of you on the line, I truly appreciate your support, and we couldn't do it without our customers, so thank you very much. A couple of things I'm most proud of. Married, going to be 20 years actually. I got to update that this year. And then father of 2 girls, probably my best achievement ever. Last few weeks, I've been working on a bathroom, which I'll show you in a moment, but I typically use SolidWorks to design everything in my life. So you might see it as a job. It's my job, but it's really what I do. It's who I am. So this treehouse I built last summer. I'm going to update it even a little bit more this summer with a couple of nice bells and whistles. But I created this in SolidWorks using Weldman's functionality. So no matter what you're trying to do out there, if you have access to SolidWorks, which as a user in a company, you can also get a home use license, please feel free to ask your employer if you could load the software at home and use it for your own projects. Get some stick time. It's only going to improve your own skills. My current project, which is coming along very nicely, is this brand new bathroom in our basement. So section 3, which we're going to be doing a week from today, I'll hopefully be posting some finished pictures of this for everybody. So the things we're going to cover in this presentation sort of dovetail what we did in the last presentation. Our 5 pillars here are innovate, design, validate, collaborate, and then manage and build. And those are the perspectives that we really look at our software when we're looking at it from the customer view. Now, for what we're talking about today and the data set that we're using, we're leveraging a data set from Myomo. And they're a SolidWorks customer that really utilizes every aspect of what our tools have to offer. Obviously, with these files, there's mechanical design, but there's also freeform shapes. There's electrical, right down to printed circuit board. And it really does encompass the gamut of what SolidWorks is useful for, which is basically everything. Now, when we're building the software, we have these pillars in mind. But as a user, you're really taking these pillars and applying them to your final solution. So for Myomo's sake here, they take our mechanical design software and they use it to create this myoelectric orthotic. It's a functioning, moving device. The electrical design enables them to use motors and actuators and sensors to be able to overcome paralysis. So it is truly electrical design in our eyes, but it has a downstream goal involved. Validation is something everybody should be doing. When critical parts are involved, we want to make sure that those parts are going to function, and especially when it comes to parts that are going to be produced in mass quantities. Validation allows us to not only find out whether our parts are going to break, but what I find almost more important is finding parts that are over-designed and being able to enhance and optimize the material utilization. So when you make a lot of parts, especially when it comes to plastic and metals, you're going to be able to save a lot of those material costs up front by designing the most optimal part for its use case. Now, collaboration happens in the eyes of everybody in a little different way. For this type of product, it really is a collaboration between everybody involved, not just the designers, but the doctors that let us know what patients' challenges are, and the patients themselves who give you feedback as to exactly how the application works, what is working and what isn't, so that things can be modified and revised as necessary. And then everything that's taking place really should have a single source of the truth, and that's management software like PDM. In this case, when you have the FDA involved, it's even some next level than what most people have to deal with, but it's super important to be able to make sure that the right people get the right data at the right time. Now, all of this has to happen, and this is everybody's company, but we got to do it as the lowest cost possible. So we want to make sure it's efficient and that it works, but we've got to do it in the least expensive way possible. So the 5 pillars that we are covering here, we're going to boil this one down into part 2. And we covered a little bit of design last time and the innovation. We're going to cover the rest of design, talk about a little bit of validation, and then we'll do a little bit of the collaboration area as well. Now, validation, I'm going to show some slides and some videos for. We've already done a full 1-hour webinar for the What's New in SolidWorks Simulation 2017, which is already available on our website. But we want to cover it here just to make sure that you're aware of it, especially for those of you who are more primarily mechanical design, but still need to dabble in the validation tools. So this is our roadmap today. we're going to do some assembly functionality, magnetic mates, which is a brand new capability with SolidWorks, and it leverages a bit of our Speedpak technology, which has evolved in a very tremendous way over the last decade. The mate controller, which we introduced in SolidWorks 2016, has some much needed enhancements based on customer requests. And then we'll get into a little bit of validation when it comes to our simulation tools, and including flow simulation and SolidWorks plastics. Today we'll finalize with a little bit of our collaboration tools, talking about a new technology called 3D Interconnect. And then finally, some collaboration from a marketing standpoint with SolidWorks Visualize, as well as a little SolidWorks routing. So let's go. First, with our assembly delighters, and we use that term a lot, but I think you get the feeling for that for those of you who've been through this a few times. Delighters are those things that you just really find are pleasant. They really help the interface. Maybe you didn't think of them before, but they really do make it for a great user experience. Our tree display, which has been getting very, very full of detail, has some new controls here for being able to clean that up depending on your needs. We're also going to talk a little bit about how component placement takes place now during mating. And it's a little bit of a better process here just based on how you select things. And then with this section here, we'll finish up with a dovetail from part 1 here, which is saving assemblies as parts, but the maintaining of the references is really the most important part of this feature. So let's get right into this data set. So what we're working on right now is this assembly. And for those of you who deal with a lot of files, maybe files that have verbose names, the feature manager can be quite a bit of an eye chart. And what we're looking at right now are things that have been required up to this point, which really do muddle the display. Well, to clean this up a little bit, we've added a few key things to our feature manager. When you right-click the name of the part of the assembly, you have the ability to go down to Tree Display. And a new option here says, Do not show configuration display state names if only one exists. So with every part, you always have at least a default configuration, and there's really no need to see that. So by triggering this option, we really do have a much more pleasant and less muddled feature manager. Now, another thing that can happen based on your assembly technique could be the deal with a lot of top-level components that can really extend the length of a feature manager. Now, you can compartmentalize these into subassemblies if it makes sense, but in many cases, this could be the subassembly where all these fasteners are sitting here in the top-level tree. So another right-click on the name of the assembly down to Tree Display gives us another option here where we can dynamically group component instances together. Now, if there are subassemblies, it's not going to reach into those subassemblies and group them here, but it's more or less dynamic folders. So as you select it, you'll see that all of the groupings of the fasteners jump into these little collapsed types of items. Now, they work like folders. The icon, of course, is very specific as to what's going on with the grouped features, but it really is a great way to be able to collapse and clean up what could be a very lengthy feature manager. Now, when it comes to mating your components, mating is one of those things that's always been very pleasant in SolidWorks, but a great new addition here actually adds some relevance to the click point where you select features. So there's a little blue crosshair on the face of this part, which is where we've selected it. Now I'm going to mate it up to this part, and if I control select it and now click coincident, those two crosshairs, those actual select points, will be joined to each other. Now, not joined in a physical way, but they are matched up with each other, which effectively gives us both a mate and a move with that operation. Much more convenient. We'll finish this up a little bit by adding some concentricities and just making sure that this motor is in the proper position. So that looks really good. Now there's some more smart placement when it comes to things like these countersunk fasteners. Now these have a tapered face to them, and with tapers it doesn't work quite as conveniently with the placement like a coincident and a concentric works on a cylindrical part. Well, now what happens when you select these tapered faces is it enables us to add a coincident relationship. Now, of course, they're the same angles as each other because of the Hole Wizard and the Toolbox library have these tapers built in. But as you place those, you'll notice that it not only puts the coincidence between those faces, but it also inverts the part to place it more properly. Now we have a little motor sitting inside this assembly, and many ways to receive this type of a data. And a lot of times it's found on a download site, whether it's the supplier site or 3D Content Central. And a lot of times we'll be given these files in a way that maybe isn't the best way to manage the document. So what I have right here is a motor, and it was downloaded as what appears to be an imported assembly. See, all the files underneath have a featureless tree. Now, I really regard this type of data in the way that I receive it. So if I'm an assembler and I get a limit switch or a motor like this, I'm really not concerned that it has shafts and bearings and end caps. I really just want this part to represent what I would purchase. So in many cases, as a file management improvement, we wouldn't want to have this as an assembly. We want to have this as a multi-body part. So I'm going to open up this file into its own window for a moment just to show you a couple nice functions for this. Now I like to use breadcrumbs. You'll notice that through my presentation here. A little tap of the D key brings the breadcrumbs local to my cursor position, and as I select those, it enables me to select subassembly depth, which in this case, I'm going to pick the motor itself. We'll open that in its own window. Now something to be very clear on with what I'm working on. I'm going to go back to the assembly for a moment here just to illustrate this. But as we look at the breadcrumbs here, one of the things I want you to see is that this subassembly has mates on it. There's concentricities and there's coincident mates amongst the parts that happen to be here. Now if we take a look at this assembly as a whole, you're going to notice that the position of this part is located based on the fastener holes on the front faces, as well as a coincidence between that front cap and this sheet metal part that we have there. Now I'm going into the assembly so that I can really dumb this thing down. I want to make it a multi-body part. But as I mentioned in part 1 of our webinar, one of the things SolidWorks is doing now is we're maintaining face and edge IDs, even though a very drastic modification to the parts might occur. So right now we have all of these mates that take place even in this assembly, and all of that stuff is going to be built into that multi-body part. So to take an assembly and save it as a multi-body part, we're going to do a file save as. Now of course this file was used in another assembly and or a drawing, so we're always presented with the save as references box. In this case, I'm going to save it as a copy and open it. Now I don't want to save this file as an assembly. What I'm actually going to do first is I'm going to change the file type to part. And this is where SolidWorks now says, it's an assembly that's going to be converted to multi-body. How do you want to address this? Either keep the exterior faces, exterior components, or all components. Now I don't know about you, but if you've used this before, exterior faces is probably the last choice I would ever do, if that. Use either exterior components or all components, and that's going to make sure you don't miss anything. So we're going to go ahead and call this one multi-body part webinar. Good enough. Now when I save this file, what you'll see is a visually perfect document relative to what we just saw right there with the assembly. And I'll tile my windows here for a moment. You'll see some other stuff we're going to cover in just a minute. But essentially what we've got now is an exact duplicate in a multi-body part versus the assembly that it represents. So the file looks great. But what happens when we address that back in the top level assembly? Well, here we're going to do a component replace. And a few years ago, we allowed you to actually go ahead and replace an assembly with a part file. So here I'm going to take this subassembly and we'll just simply replace the component. Now we're going to take the assembly and we're going to replace it with the multi-body part that we just saved. But the key here is that we are going to reattach the mates. Typically a check mark I would remove in this situation. With reattach mates turned on, what you'll notice is 5 beautiful check marks. And what that means is we've now swapped this file out. Instead of it being an assembly, it's a multi-body part, but we didn't lose the concentric mates in the fastener holes, nor the coincident mate on the front face. And this is a fantastic feature. You're going to see this emphasized a little bit later in 3D Interconnect. Now a few additional things I wanted to make note of here is, first of all, any mates that have dimensions associated. So limit and angle, whether they happen to be limit distance or just distance mates, or the width or slot mates if you happen to have them set to percentage or distance. You can basically set these mates now to a driven value. Now much like a driven dimension in a SolidWorks part file, this is a dimension that would react to other dimensional changes or part position. But the usefulness here is that that dimension might also be used to solve other things during equations. And that makes it nice and convenient that it can sit there and react, but then itself be used as a solver in other locations. Now this might look like the measure tool to you, but this is actually the distance mate between cylindrical bodies. Now we have a very similar method here that we can now use that's the way that we would measure cylindrical bodies in an assembly or a part. And in this case, we can now mate them either center to center, which is the distance default. We can also say minimum distance, which would be the tangencies closest to each other, or maximum, which is going to be the outside edges. Now there is a fourth option here, which is a mixed bag. You could go to the minimum edge of one and the maximum of the other, just based on whatever the circumstances dictate. Also a great enhancement added to 2016, but not always a perfect use case, was the ability to select a hidden component in the Feature Manager and see that component as a transparent preview in the assembly window. Now, this is great for most files out there, but we've noticed a few customers that are dealing with very heavy documents, imported data, very complex parts, and huge surface bodies. And those do add a little bit of a performance hit to it. So there's a new option that allows you to enable or disable the hidden preview transparency. Assembly visualization is a great tool for looking at your assemblies in a whole new way. Now, ways we've done this up to this point were the ability to sort your components either in mass, highest to lowest. In some cases, we would sort based on columns of properties like ownership and workflow state if you're using PDM. Great way to see what parts are in what states, and they even colorize on your window. Well, a new thing that we've added here to SolidWorks 2017 is sorting the parts in their last registered open time. Gives you an idea of which parts are heavier in the system and exactly what's taking place with those. Now, I'm going to go back to this assembly for a second because I want to show this file. It's an important thing here because I'm not going to show open time. That's just one of the new ones. But one that I really like to use on this is graphics triangles. If you go to the Evaluate tab, you'll see Assembly Visualization. Now, it pulls the parts up immediately and it puts them based on the criteria. In this case, the default happens to be mass. So if we sort on that, we're going to have the highest mass parts followed by the lower mass parts. Well, I like to go ahead and take this column here and add a new one. We're going to go to More. And in this case, if you're having an assembly with a lot of performance issues, you can choose a SolidWorks calculated feature here that's simply called Graphics Triangles. Now, what we do with those graphics triangles is we basically go ahead and sort this part based on its stress level on the actual, I'm looking for it now on the list, sort this file based on the actual hit of how many triangles are going to be shown in this file. Now, this is what your video card sees. So when you pick graphics triangles and you say OK, we have the most offensive part in this assembly at 51,084 triangles, and there are 2 of them. When you select it, you will get bidirectional feedback, but the shocking part is this. If you noticed, the part that highlighted is this tiny yet huge graphical bearing. And all of those spheres on the inside are creating thousands upon thousands of unnecessary triangles. Now, this is a situation where we could easily open this bearing in its own window, either hide all of those spheres or extrude a rectangle or circle over top of them and basically minimize this part down to the small number of triangles that it should represent. But this is a key example of the type of thing that we see when an assembly isn't performing up to snuff and you're not quite sure why. There could be a very small part in there causing a very big problem. I want to move on to magnetic mates. Now, this is a coupled feature with our Speedpak tools, and Speedpak's been around for quite a long time. But what happens here is you're basically setting up files so that they can be picked, dragged, and snapped into place off of a library. We use an asset publisher to be able to determine location and normal direction for the parts so that we know how one snaps to the next. Now, during this, we use Speedpak in a lot of these cases where these assets can be included, as well as any other detail, body, face, or feature that you might find important enough that needs to be active in the math body. Anything that we add to the Speedpak would be useful in mates and dimensioning on 2D drawings. Now let's go ahead and do that, jump past my slide. So we're going to open up SolidWorks one more time, and I'm going to jump over to a very large assembly here, which happens to be a plant layout. Now, this plant layout is several thousand components, and you can see that it rotates pretty nicely on the screen, though I'm sure we're getting some degradation because of the bandwidth across of our GoToMeeting. When we're using our magnetic mates, we're basically just dragging components into place, and I'm going to do that by inserting a few additional components. When we select Insert Components, you can go ahead and browse for parts, or you can select them directly off of this view. For this one here, what I want to do is just go ahead and grab my spur conveyor. Now, there are setups in this which determine automatically the mating to the floor, which it's positioned, but we also see these magenta dots show up. And when you get a particular distance from those magenta dots, the mate starts to grab hold. Now, it's not going to go ahead and actually put the mate in until I select or click on the screen. But once I have my part in position, I can go ahead and click, and it will then continue and mate those 2 dots together. So I'm going to do one more of these just so you can really see what's happening here. Now, as I drop the component in, a simple touch of the tab key would allow me to toggle position, so I can rotate that at 90-degree shifts. And again, when those dots find the awareness of each other, we can select and it will simply put that mate in. Now these things can be selected and detached if necessary. So if I have another conveyor section I'd like to move, I can rip that magnetic mate away, and as soon as it's closer to one of these other dots, I can let that mate come into play. Now typical Windows does work here as well, which means copy and paste. So if I hold the Control key down, I can take a second instance of this pick and place robot, and I can simply snap it over to the second instance of this assembly line. Now as I drag things into place, I'm sure you're seeing that the performance on this is pretty stunning. We're dragging lots of parts around, we're snapping them into position, and they're moving in a very predictable way. The mates that we put on during the asset publishing allow us to go ahead and control the positioning. So as I drag a component around like this, if it's sitting in the relative position it needs to for that mate, that's great. But once I go ahead and put one that's not quite in the right position, it will normalize or change the attitude just based on how the magnetic mate happens to be built. Now everything that we're doing here is actually utilizing our Speedpak technologies. And for those of you who use this, you might notice the tiny sort of yin-yang sphere next to my cursor there. And that's something that indicates that my cursor is over a mix of hidden and shown components. Now I'm going to go ahead and toggle my Speedpak circle, which I typically do in Tools and Options under Display. But here with a little hotkey, I can go ahead and show you that X-ray vision that we give you with Speedpak to let you know what is in fact loaded into the math footprint and what is really just there based on your video card. Now we set these assets up using these types of techniques. And if you're unfamiliar with what Speedpak is, it really is just a sub or derived configuration of the full-up mathematical configuration. Here we see the entire default configuration, and then below that there is a Speedpak variant. Now as I hover over this assembly, you'll notice that just the curved rails are actually loaded into the math footprint. If I then double click on the full up configuration, in this case it's going to load the math data for absolutely everything. So it's very easy to fluidly move in and out of the Speedpak variant. Now to build up the magnetic mates, we do this by using our asset publisher. Now the published references here are really just based on selections and positions. The top plane is dictated as the ground plane, which it's how it knows how to go into that large assembly. Well, we also have different connectors here, which are based on selected points and normals. So down here in the lower left-hand corner, we have a simple center line, to which we have a point right at the midpoint, and then the direction of our normal is facing outward. So that way when it mates up to an adjacent component, those faces mate towards each other. As far as Speedpak goes though, Speedpak can go ahead and use these assets as well as anything else that you deem is important for mating and dimensioning. When you make a change or add a new Speedpak to your configurations, you get a window here that allows you to select those things that will be available. And you can fluidly edit this if you find that you're trying to make a drawing and you can't dimension to the faces that you wanted, or you're trying to put mates on and those faces aren't active. So here you see we have full components that have been placed in here. We've also got all of the connectors in the ground plane from our published assets, as well as a sketch that's for positioning purposes. But we can choose to include anything we find important as well. So if I go ahead and add in, say, the foot pads to the bottom of these faces, and maybe I want to mate up to this motor, so I might go ahead and select the front face of that motor and have that as something that's available during Speedpak as well. Once I say OK to this, what you're now going to see with my Speedpak circle showing is that the side rails are available, but now down here on the floor, you'll actually see that the feet at the bottom of those rails is also there. And then over here by the motor, the front face as well is available. And that means that these faces are going to be available in a drawing or in an assembly so that they can be mated to or dimensioned to. So Speedpak is one of those tools where if you haven't looked at it lately, it is definitely worth your time to go ahead and look at it again. The mate controller was introduced in SolidWorks 2016. And what happens with the mate controller is it tries to replace those situations where users make configurations in order to show different positions of a moving assembly. So if you make things like extended or retracted configurations, or even a higher level like this pick and place robot, the mate controller is a great tool to really keep your file size efficient, but allow you to capture these positions in a very simple way. A couple of other side benefits to this are animation and the ability to go ahead and show this in an e-drawing. So I'm going to cover each of those. Now with this pick and place robot, Any dimension, or excuse me, any mate that has a dimension associated with it would be useful inside of our mate controller. Now what you'll see inside of my mates down here is that we've taken a lot of these angle and distance mates and we've simply slow double clicked them and changed their name to something a little bit more auditable. Just makes the user experience on this a much more pleasant thing. Now in the feature manager is where the mate controller feature sits, and there's a button for it on your toolbars, but I've already got that one started here, so I'm just going to show you how this works. When we edit the feature, what you'll notice is that all of the mates that have dimensions are selected up in this box. And as such, you're going to see an individual line item with that dimension's value available to modify. Now at any point, we can go ahead and make new positions. We have several that are already here that I can toggle through. You'll notice that each of the values of the dimensions changes in a different combination in order to capture these positions. Now I can easily go ahead and make a new position by clicking this button here. You can name it whatever you'd like. We're just going to stick with position 11. When I go ahead and move dimensions in the sliders, that's my ability to go ahead and make changes through the property manager area. But you can also go ahead and unlock dimensions over here and then simply action on those graphically in order to capture these different changes. You'll notice the slider in the property manager is reacting to my changes. Now if I like the position here, I'm going to refresh it based on the new values, and then we're just going to go ahead and be able to toggle between others. So you'll notice that as I go through the pick, place, drop, and retract, we're also going to get to position 11, which is right there, the position we just selected. Now everything that we're doing inside of this tool is now something that, if need be, we do have the ability to capture configurations. So there's a button that's been added next to the Positions tab that allows me to grab a particular position. So in this one here, we're going to go ahead and go to the pickup position, and we'll capture a configuration. We're going to go to the home position here. We'll capture a configuration, and then we'll also go ahead and picture one over here at the open grip. And you'll notice that as I do that, it's added configurations to my configuration manager, but it does indicate that those were added based on mate controller positions. The reason these are important is because when I go to a drawing, I still need configurations in order to register and hold a different drawing view from one to the other. So by selecting in these drawing views, I can select this one and go to my pickup position. My home position is going to be right here in the middle, and then over here is my release position. So configurations are still necessary, but we can limit the amount of overhead that they produce by simply using the mate controller where necessary, and then configurations where it has to be. Now one side note on this is that when we're dealing with our mate controller, we have a couple of additional benefits. One benefit is the fact that down here at the bottom, you can determine what timestamp it takes to go from one position to the next. And that's a very effective way to make an animation. Now this animation can easily be saved out as an AVI file just by clicking this button. And if you happen to have Photo View 360 turned on, that would also enable you to output a full photorealistic rendered animation based on this tool. But one of the things this does not do is it does not trickle down into e-drawings. Now down here in the Motion Study tool, this is the tab that we put different types of keyframe-based animations in. You'll notice that if I expand this out, all of these mates have absolutely no keyframes. Well, this tool here is supported as the animation tool inside of eDrawings. Where you can bridge the gap is by simply going to the wizard. And when you make a wizard, the Mate Controller Inputs is a selectable tool to produce this wizard. So when I tell it simply where I want it to start, 0 seconds, and the duration, which is 10 seconds, it'll automatically produce all of these keys based on my Mate controller. Now if I save this assembly and open it with an eDrawing, this animation will be fully supported in that eDrawing output. All right, so let's move over now from design into a little bit of validation. Now validation really should be done on any critical parts. But as we're working on different parts, they all have a different criteria of how you might want to verify their capabilities. So we're going to start in SolidWorks simulation. One of the most frustrating things I've seen happen and have had happen myself is that I'm going to go to a meeting, I'm going to spend a couple of hours there, and in order to maximize my time, I want to set up a simulation while I'm in the meeting. Well, many times users find that when they return from that meeting, there's a box waiting for an action. Well, SolidWorks 2017 changes that. We now have automatic decision making, and it'll take the last decision that you made on these boxes and in 30 seconds simply continue on. So in this case, if you have a large displacement question or a direct solver message, it's going to use the last thing that you did and it's going to simply continue on. No more frustration coming back from a 3-hour meeting to find out your computer was waiting for you to say yes. Stress hotspots are also much easier to see. We kind of gray out or make transparent the rest of the body and really emphasize the location of where these hotspots happen to be. Colorizing of these charts also improves this. In this case, what we're seeing is yield strength, and anything above that happens to be pink. So it's very easy to see all of the areas that need to either have a thickness added to them or maybe even a different material in order to have a higher yield strength. We also have easy methods to convert basic static studies over to a nonlinear or linear dynamic study, as well as the ability to show things like these plotted and or deformed plotted features and parts within your real SolidWorks assemblies while you're working. So first, if you have a study, you can right-click on the tab and say Convert. Now, converting that study is a simple matter of taking your static study and switching it over to a nonlinear or a linear dynamic. All of the loads, boundary conditions, and setup will transfer across. You simply need to choose it, maybe set it to a nonlinear type of material that has the proper stress-strain curve, and then from there, you'll be able to go ahead and easily run that nonlinear analysis. In this case, we're going into an ABS plastic, and of course, plastics are the types of components that are in the wheelhouse for a nonlinear analysis. For showing simulation data on a plot, this really leverages a lot of the RealView technologies we already use. You simply select the plot that you've selected, and it will put a hybrid texture over top of the part. If you'd like to show it deformed, that's also another checkbox away. This used to take in the past a whole lot of work in Photoshop to be able to meld two different images together to get this type of effect. Simply done here. On top of this, we have some new capabilities to offload simulations onto other computers. By installing the SolidWorks Simulation Worker agent on another computer and utilizing the Intel Network Sparse solver, it'll go out and grab those other computers once the solver has been triggered, and it will run it on a different machine while you sit and continue to set up different studies. For flow analysis, some great enhancements here include using low-level components as a condition for a higher-level simulation. The beauty with this is that we can run a simulation on, say, this motherboard here with all of its chips and components. And then when that is done, we can use it as the input in this higher-level simulation you see in the upper right-hand corner. That way, we don't have the overhead of having to simulate all of these meticulous components at the top level. It simply has a finished result that then becomes that input. We've also added multi-parameter optimization for flow studies. Now, this is something we've been doing in simulation for quite a while when it comes to optimization. You're basically giving it a few dimensions that are variable and the ranges to which those dimensions can change. Simply hit run, and it will start changing those values and rerunning the simulation in order to converge on the appropriate result. How far are they from the flame, and what is their angle to that flame? All we do is input these three variables and say go, and flow simulation will then start to change the numbers and check the simulation. Our goal here is to optimize velocity at the top of the vortex of that flame. So what you'll see as we add additional flames or additional fans and get the angles just right, we have now converged to the maximum velocity at the red area that you see on the flame. So it's a great way to put in what can happen and not have to sit there and deal with the minutia of the change and the rerun. As far as SolidWorks Plastics goes, we've got some great additions here that have to do with some other things we've had for a while, like intuitive weld line display. Now, weld line display is nothing new. All the products that do plastic injection molding have this. But our weld line display lets you know what angles those flow fronts meet. And when you have a flow front that means at a very sharp angle, definitely what's going to happen at that is those flow fronts will hit and sort of deflect off of each other and not really meld together. When they hit at a very flat angle, those flow lines are going to go ahead and overlap each other and really converge into a nice clean set of the plastic. So it's important not just where weld lines are, but the angles at which they meet will have a lot to do with the ultimate quality of your part. We also go well above and beyond just simple mold fill. Here we actually have cool accuracy, which means we're going to hold the part and we're going to pack it until the time at which the part cools and the residual stresses in that mold can release. If you pop that part out too quick and it's still too hot, the part's going to sit on the table and warp right before your eyes as it cools. So again, we are not just a mold fill application. We bring it right down to the full cycle of any part. And this is where you can get efficiency, good parts or bad parts, just by leveraging a few seconds here and there. When we're talking plastic injection molding, it's all about time and throughput. As I mentioned, we've already got a What's New in SolidWorks Simulation 2017 webinar that's an hour long, and that is also located on our webpage. So the last section we're going to cover today is going to be a few of our pieces of the collaboration tool. We're going to start out with 3D Interconnect. 3D Interconnect is most simply described as translatorless translation, and that's exactly what I said. We're going to utilize data from other systems, but we're not just going to bring it in as neutral bodies. We're actually going to reference the files in the original systems. Now, there's many different ways that this thing works, but the theme is native opening of third-party design data from a lot of other CAD tools. We are not translating it, we are referencing it, which means changes that happened in the original system will trickle into SolidWorks. Now, we also, as I mentioned before, keep face and edge IDs. So if we make edits to those parts in SolidWorks and then in the original CAD system they change, the edits will most likely fluidly update in SolidWorks. The file types that we're currently doing with this are our primary competitors. So PTC or Creo, depending on how long you've been calling that product its name, Autodesk Inventor, Solid Edge, UGNX or Siemens NX as it is today, and then CATIA V5 if you have a SolidWorks Premium license. Now this is an interesting side note because what many of you may not realize is that with SolidWorks 2017, if you own a SolidWorks Premium seat, you now have the CATIA V5 translator. Instead of putting it out there as an extra purchase, we've now just baked that into every SolidWorks Premium seat. In this case, you'd need that if you're opening CATIA files using 3D Interconnect. So there's three different processes that I'm going to demonstrate here. First is the direct insertion of the files from the other systems into the SolidWorks assembly. We'll mate it up and use it just like we built it ourselves. Second, we're going to open the file up as the more typical way, which is a base or derived part. We open the file, we're going to make some changes to it, and then that file is also going to change in its original CAD software. And then finally, the most traditional way is just opening an imported data and breaking the link all together so that we can either modify it or add things to it as necessary. In all cases, preserving face and edge IDs. So let's get right into this. First thing that we're going to cover is direct insertion. Now I'm going to take an Autodesk Inventor file and use it in my SolidWorks assembly. Let me get my switches reset and we'll get this open. So my goal once again is to not have to translate the files, and this is going to help performance as well because we're not holding and dragging along these inefficient non-native data sets. So I want to go ahead and take this file here and we're just going to rotate this around a touch. Now, insert components is how we're going to do this. So we're not going to open this file up in its own window. We're just going to insert it directly. And when insert components is clicked and there are no other files open in the session, it jumps right to the browse button because, of course, that's the next logical step. So on this one here, what I want to do is go ahead and show you how to do this, but I've got to do it in sort of a creative way. We're first going to go ahead and open up an Autodesk Inventor assembly. But as you can see, V5, Pro E, Edge, and Inventor, and UG are all on this list. So we're going to take our Inventor assembly. Now when I click this button, this will take about 5 seconds. So click, 2, 3, 4. Perfect. So performance on this is pretty quick. What happens in the Feature Manager is you'll notice that the file name itself still is listed as the name it was when we opened it, but it's got the Inventor Assembly extension added to it. There's also a tiny arrow on that icon, which indicates that this file is looking externally for its definition, as is the same type of icon for all of the parts. If we look inside this assembly, you'll notice this battery pack has 8 batteries to it. Now it comes in with all of its reference geometry, and this is usable. You can take the right plane here, the right plane here. We're just going to go ahead and mate those up symmetric to each other. We're going to go ahead and select through our part right here, and I'm also going to go ahead and select the back face of this assembly. We're going to mate it up to the front of this rib. Now, final location on this one, I'm going to go ahead and use this right down here. We need to grab this battery terminal and the face that we've got right up there, and we're just going to mate those tangent. Now another mate that we have here is really to illustrate a point, and it has to do with this sheet metal bracket on the front. You'll notice the battery pack is very narrow compared to where this bracket is positioned. So we're going to go ahead and take the back side of this bracket, and we're going to go ahead and mate that up with the front side of our battery pack. There are in-context features of the holes and the subsequent rivets that are mated into those holes, which will have to move as a result of this in-context feature. And there you have it. Inventor assembly brought into a SolidWorks assembly and kept native, but used as if we designed it ourselves. Now what happens in Inventor is the user continues to work, and what's happening there is he's making changes and he's hitting save. Simple as that. Now I don't have Inventor on my machine, so I can't make that change live for you, but I'm going to show you exactly how we illustrate this change. By going into Windows Explorer, what I need to do is actually access that folder. And this is the folder we're looking at, our supplier parts. Here are the Inventor assemblies as well as a few other, and I need to go ahead and simulate this by copying over the new version over top of the old. So my second version of my battery pack, I will simply copy and paste over top of the one that I've referenced, as if the Inventor user has now changed and saved the file. Now back in SolidWorks, it all looks the same until I hit rebuild. And what you'll see is that this icon now takes a different change, and there's a small rebuild icon showing. As far as the user is concerned, I just have to right-click and say Update. Anything that changed in Inventor will now show up in SolidWorks, and all the face and edge IDs will be maintained, including the in-context relationship to the bracket on the front. Once again, this file never has to be translated fully into SolidWorks data, and it can always sit and reference the original CAD data, even when PDM is used. Now the second method we're going to do is we're going to open up a Pro Engineer part, and we'll use that inside of our assembly in a normal environment. So let's go ahead and do that. So in this case, I'm just going to do a basic file open. We'll browse to our file here, and we'll just simply open our Pro E component. Now what happens is this file opens up in its own window in more of a traditional method, yet it is still referencing the external file. Now I'm going to go ahead and make a change to this document, and we'll do that in a typical way that I would take when it comes to gears and sprockets. I've got some design library elements over here that I want to utilize, and this is not only to go ahead and make it more of a realistic circumstance, but also show you how the referencing maintains and updates as we go. So I'm taking a feature and I'm dropping it on a face, and that gives it a relationship just right there. But when we locate design library features, we also have to pick relevant edges in order to locate and position these. So by grabbing a circular edge on the inside of the part, it will position my keyway and also auto-locate it based on the diameter of the hole. Great. And now I'm going to go ahead and put in a curved slot. Now this slot is huge compared to the preview that I've got here. When I drop it in place, the outside edge of it will be co-radial to whatever edge I select. So I'm going to go ahead and pick an edge here, and it will size down and put my curved slot exactly where it needs to be. Great, let's go ahead and save this file and move on. So I'm going to take this document and we'll just do a little smart mate here from one file to the other. Just grab the circular edge, drag it into the assembly, and there it goes. It's now mated up and it moves very, very nicely. However, this is where we start to see whether it's truly going to work for us or not. Now when we find a problem like this is typically when we get on the phone with our supplier and tell him we need to make a change. Well, the way changes take place in Pro Engineer is they add a numeral to the end of the file name, and this is version control, whether you're using their PDM tool or not. When a Pro E person changes the file and hits save, it makes a new version by adding a new dot to the end of it. So this is what we're going to illustrate now by using our Windows Explorer technique. So with this file right here, I have to simply have that part 2 adjacent to the part 1. So again, we'll go into our alternate versions. This time we'll pick our part 2, and I'm simply going to copy it so that it's in the same folder with part 1. Now back here in SolidWorks, you'll notice right here this icon once again. Once I hit rebuild, you'll see that it now is aware of the second version, and from there it's going to give us our rebuild icon. A right click once again and an update will yield not only the new geometry but also the changes made to the features that I added. Edge IDs update, the file updates within the assembly, and everything looks fantastic. So very much a hybrid environment if you do happen to have those multiple tools within your facility, or you receive data on a regular basis from users who actually utilize these tools. So the last method we're going to show here is the more traditional method, where we're going to import data and then we're going to break the link. But once again, face and edge IDs are preserved through this entire process. So back in this assembly, let's go ahead and insert components one more time. We'll browse, and this time let's go ahead and select a solid edge assembly. Once again, performance is very fast, so when I click OK, I wait just a few seconds on this assembly, and there it is, right where I need it. Now, utilizing very basic snap-to-fit SmartMates in SolidWorks, I'm just going to use my Alt key. We're going to pick and drag our part into position. It's not quite the direction I want. Tab key will take care of that. And then let's just go ahead and finish locating it. Concentricity in a couple of places, and that looks pretty good. Now, this is where I start to validate this imported data to see whether there are fit or alignment issues. Now, the fastener holes look pretty good, but I think you can see right here, these two holes just do not match up with each other. Now, this is the point where I either have to decide, do I want to get the supplier involved, or do I want to make the change myself? Well, here we're going to make the change ourselves. To do that, though, we have to sever the link to the original data because we are going to make a one-off as a result of this. So you right-click on your assembly or your part and say Break Link, and it will remind you that this cannot be undone. For the part that I want to modify, we're also going to right-click on it and also say Break Link. Yes, it cannot be undone. The purpose on this one is that I want to take that part and I want to run some feature recognition on it. Now, for those of you who are unaware, every license of SolidWorks has FeatureWorks, Standard, Premium, and Professional. Now, to do it, you can either right-click on the full part and run FeatureWorks right through the menus, but it doesn't have to be an all-go or no-go proposition. A simple right-click on the feature you'd like to edit and an Edit Feature will actually run FeatureWorks dynamically and translate that feature into full parameterized data. We've got one here that's the right size as a whole in our Hole Wizard library. Therefore, it gives us Hole Wizard functionality. That said, I can now go back into my assembly, identify where this part is, and then go ahead and make a change to that Hole Wizard feature. Here, we're just simply going to go ahead and edit the sketch. We'll toggle this thing over to wireframe briefly so I can pick the edge out from behind, and we'll just make those concentric to each other. Perfect. Now my hole's been modified, its position is proper, located based on the hole it needs to mate to, and everything looks great. So those are three very distinctly different methods of utilizing third-party data, whether it maintains the link to that third-party data or whether you do the traditional methods of breaking it. But you can see the flexibility and the versatility of being able to make changes and not lose mates or other broken related features when those types of things happen. So those are pretty great. All right, on to SolidWorks Visualize. Visualize was added in SolidWorks 2016, and though it is a separate product that runs in a standalone window, it does not cost users of SolidWorks Professional and Premium anything more. In fact, Visualize came with both of those products. Now, there's also Visualize Professional, which you can bolt onto any seat of SolidWorks, and that enables things like animations, render farms, and some virtual reality functionality that's pretty fantastic as well. The things that we've added this time around were some new plugins that connect SolidWorks and Visualize together, but also this new network rendering capability called Visualize Boost. Now, even though we're tossing the SolidWorks assemblies out to Visualize to be rendered, motion studies created in SolidWorks assemblies also transfer across, and those are useful in any type of animation, like an explode, collapse, or the mate controller thing that you saw me do just a while ago. We also have new camera navigation, which is the same as you'd use in SolidWorks. So if you are a dual functionality person who has to do rendering, scroll wheels and clicks and right clicks will work the exact same way as they do in SolidWorks. And then some transparency and cutting plane animation capabilities. So for Visualize Boost, you need a new serial number. You go ahead and load that up on the computer, and what that will do is then take the rendering off of the computer that's actually producing the SolidWorks Visualize data. So farm rendering, so to speak. What also is happening these days is, based on your video card, of course, you're going to get more bang for your buck when it comes to rendering. And this is where things like multi-cores and multi-threaded functionality really get leveraged. Well, you notice in these different levels of the Quadro video cards here, you're also going to get different performance capabilities. And in some cases, GPUs, most cases actually, are better than CPUs. So in many server applications, they're loaded with NVIDIA video cards as opposed to motherboards with Intel processors. Now Visualize only uses Quadro shaders, NVIDIA files or NVIDIA software. So if you do have an AMD or an ATI, please get a hold of us and we'll talk to you about the options there. Now this is an animation based on a motion study that was done in SolidWorks. Little tabletop rotate as well as the explode and collapse steps along with a little bit of rotation. That was produced in SolidWorks and rendered in Visualize Professional. Simple check mark here allows us to have our mouse wheels and buttons work exactly the way they do in SolidWorks, which helps from a comfort level standpoint for sure. Now this animation is a transparency animation, so you can see the part slowly fading away. But one of the things that just never ceases to amaze me about this tool is the absolute quality of these renderings. When we do the section view here, you'll also get a great feel for that once we reveal the lights on the battery pack itself. The nice soft glow of those LEDs really gives you, again, a great feel for not only the quality of the lighting, but also in this case the depth of field as the part fades and gets blurry as it goes out from the center point of focus. Didn't really have a good transition here, so let's picture one of my chickens. All right, SolidWorks routing. Last thing that we're going to cover today. Routing is a SolidWorks premium operation, but it's one of those things where it really enables those users that do piping and conduit and hose runs and electrical very often. It really gives you a very powerful automated process for making these things happen. Now this time we've added new piping libraries in the form of these nipple libraries. Now these work differently than a normal fitting does because with a nipple you're talking about a threaded component. And most of the component libraries we have that are full of T's and elbows and reducers and other types of fittings, they're going to go on the inside or the middle of a run. Now what happens when we drop this nipple there is it's going to segment the pipe back to the proper connection points as you'd typically see. But we can also go ahead and right-click on this and simply remove that part of the route because the nipple itself is threaded, that piece of the pipe is unnecessary. When I do that on both sides and say OK, it will finish with the fitting and the proper thread engagement for this set of threaded tubing with elbows. There's some other auto route enhancements when it comes to just the component layout tools, as well as automatically zooming to fit in tools and options after you add additional routing components. This is very convenient as your route grows while you create it. Now along the lines of you don't know what you don't know, this is an interesting one to me right here. We have the ability now to create exploded views of routed assemblies. The you don't know what you don't know part is that I didn't know we couldn't do this. I guess I just assumed we could. So this time around, what we can now do is take a routed assembly, which is, different technologically than a normal assembly that's made it up. So I guess it does make sense. But essentially a route is based on a 3D sketch. Here, we take the routed assembly and we use typical explode techniques that you would use in assemblies or other multi-body parts. So once again, didn't know we couldn't do this, but I sure am glad we can. All right, almost done. That looks pretty good. Good. Last but not least, we're doing more when it comes to electrical inside of routings, and a much needed enhancement here is the ability to flatten what we call a disjointed route. Now, disjointed routes are those routes that just don't simply have a point A to point Z set of connectors. In this case, we're going to see wires of the main harness go into a big clip, and then from that clip, additional leaders go out to other clips, jumping to power, jumping to ground, or jumping to signal wires. Now, these are really dynamic, but they're also quite common, which is why it's a very important thing for us to have these. In the Myomo assembly, we have a main wire that's going from the front actuators back to the motor, battery, and circuit board assembly. Now, this is where we're going to see our main clip, but that clip is going to go ahead and have some sub-routes off of that. Now, anytime we take a route inside of SolidWorks, the purpose of doing this in 3D is, of course, to get those real 3D lengths. Because though you can make these in a schematic all day long, you just know what pins go to what pins and what components go to what components. But you never really know the physical length until these things are made. So in order to nail board this properly, you really do need to have these distances. Now when I flatten the route, I can either show it as real distance nail board verifiable, or more of a schematic mechanical layout so that we know what components lay in what positions and again where the pin alignments happen to be. Either way, shown in this more schematic method is still going to yield a bill of materials on the drawing that does give us those true cut lengths. Using a drawing like this, an assembler should be able to walk up to a spool wall, pull all of these wires in those quantities and those lengths, and then sit down at a table and assemble this harness with the proper fit and function. So Myomo's been using SolidWorks since about 2002. They've had a couple of different iterations to the product, and now sitting here at 2017, although 2015 was the last release product, they've got another one in pre-production. But they've really been able to enable SolidWorks, use SolidWorks to enable their designers to create not only more aesthetically pleasing products, because as they evolve, they're going to have to be a style item since users are wearing these things, but also much lighter, much stronger, and just a better evolution of the product with each iteration that they get. So we've covered these 5 topics. We're going to finish up with collaboration in part 3 next week, as well as the manage and build part of this. But SolidWorks truly does encompass every aspect of the design process, from upfront right down to validation, data management, and also the ability to do all of the electrical, freeform surfaces, and mechanical design necessary for a product such as this. So this is what we covered today. I want to invite you back next week for another 1-hour session that's going to cover part 3, where we're going to tackle e-drawings, treehouse, a little bit of our costing, and then the ability to deliver these types of products through drawings, model-based definition, how SolidWorks PDM has now evolved, and then changes happening with SolidWorks inspection. And then finally, we'll wrap up with the state of the state as 3D printing is now, because it's a dynamic and ever-changing process. So something you won't want to miss. So I want to thank everybody for spending an hour today with me. We recorded this, so we'll place it up on our website. So once again, tell your colleagues to be able to watch this at their leisure anytime they would like. So with that, I want to say thank you very much for spending some time with us. And please contact us if there's any questions that we can help you with. Have a great day.